Welcome to this explainer. Today, we're going to demystify the somewhat abstract concepts of software design and explore what I like to call the quest for the perfect module. I mean, if you've ever stared down a massive, sprawling codebase and just wondered how to keep it from collapsing under its own weight, well, you're absolutely in the right place. So let's take a quick look at our roadmap. We'll start with the foundation of software design, jump into the magic of modularization, compare coupling versus cohesion, and then break down both the spectrum of coupling and the spectrum of cohesion.
All right, starting right off with Section 1, the foundation of software design.
So what are we actually talking about here? Essentially, design is that absolutely crucial bridge between what a user wants and the actual code the programmer sits down to write. It takes those abstract, sometimes fuzzy desires and molds them into a concrete blueprint.
And this process builds across three distinct levels. You start way up at the top with architectural design, you move down into high-level design, and finally, you zoom all the way into detailed design, which is where all that precise logic actually lives.
Moving right along to Section 2, the magic of modularization.
Think of modularization kind of like untangling a giant ball of yarn into neat, totally separate spools. By dividing a massive system into discrete, independent units, we unlock some pretty incredible benefits. I mean, let's be real. Smaller components are just vastly easier to maintain. Plus, highly cohesive parts become these great reusable building blocks. We even get some solid security benefits and the ability to execute tasks concurrently. Basically, you can run modules in parallel to speed the whole shebang up.
Which brings us to Section 3, coupling versus cohesion.
So how do we know if we actually did a good job splitting things up? You really got to constantly contrast these two concepts in your mind. Coupling is an intermodular measure. It's the strength of interdependence between different modules, and we want this to be as low as possible. Cohesion, on the other hand, is an intramodular measure. That's the strength of the relationship between tasks performed strictly inside a single module, and we want that to be super high.
If you visualize this, those strong, solid blue bonds inside the boxes, that's your cohesion, keeping internal tasks tightly unified. But those dashed red lines stretching across to other modules, that's your coupling. For a truly resilient system, you want a ton of strong blue lines and very, very few red dashed ones.
All right, diving into Section 4, the spectrum of coupling. Before we get into the exact types, just ask yourself, if modifying one single component breaks literally everything connected to it, how hard does your job as a programmer become? When dependencies are that high, your modules have to be understood together, changed together, and debugged together. It turns into a massive headache really quickly.
So here is how that coupling hierarchy actually shakes out. At the very top, you have the highly undesirable content coupling. As we move down, things improve through common, stamp, and data coupling, until we hit the absolute best-case scenario at the bottom, message coupling. That's where independent modules just smoothly communicate via simple message passing.
You can actually see the structural difference. On one hand, you have a well-designed, loosely coupled system. On the other hand, a tightly coupled nightmare where everything shares a massive single data area. In that tight system, one tiny change to the shared data can trigger cascading failures across all your modules at the exact same time.
Let's zoom in on a specific, super common pain point, stamp coupling. This happens when you force a component to know about complex data structures it absolutely doesn't need, just so it can grab one tiny piece of information.
For example, imagine passing a massive, complete student record to a simple module whose only job is to calculate a GPA. That record might have medical info, home addresses, emergency contacts. Passing all of that just to do some math creates this highly unnecessary risk. If the format of the address data changes down the line, your GPA calculator might suddenly break for literally no logical reason.
And then, at the absolute worst end of the spectrum, we have content coupling. They actually call it pathological coupling, which tells you everything you need to know. This is when a module directly accesses or modifies the internal workings of another module. It makes the system nearly impossible to fix without breaking 10 other things.
Just look at this structural chaos. You've got code jumping with a goto statement right into the middle of another component. It completely obliterates any boundary between the modules. If that target component ever changes its internal structure, the jumping component fails instantly. You're basically just writing one giant messy script and pretending they're separate modules.
All right, let's flip our perspective for Section 5, the spectrum of cohesion.
Just like coupling, cohesion is a spectrum. But here's the twist. We want to strive for the absolute highest levels. We want to run away from arbitrary, low cohesion groupings at the top and work our way all the way down toward functional perfection. The weakest link here is coincidental cohesion. This is where code is basically just shoved together for no real structural reason. It's kind of like when a developer creates a utilities class. Let's be honest, that's just the software equivalent of a messy kitchen junk drawer where you toss whatever random functions you need for the day.
To see why this is such a nightmare for maintainability, imagine one single module that prints a line of text, reverses a string, and then calculates some complex floating point math all at once. Because it's doing totally unrelated actions, it degrades maintainability and virtually guarantees you can never reuse it anywhere else in the system.
As we step up the ladder, we start adding actual intent. First, parts might be grouped logically, like putting all input handling together. Or they might have temporal cohesion, where they're grouped because they fire at the exact same time, like system initialization. We get even stronger with procedural cohesion, which follows a sequence, or communicational cohesion, where parts operate on the exact same data record.
But then we hit the absolute gold standard, functional cohesion. In a functionally cohesive module, every single line of code serves one master, well-defined task. Think of a module whose sole purpose in life is to validate an email address format. It does one thing, it does it flawlessly, and it doesn't care about anything else going on in the system.
So, as you wrap up this explainer and head back to design your next software system, I want to leave you with this thought to measure your success. Look really closely at the code you've grouped together. Are your modules acting as highly cohesive, independent experts? Or are they a tangled web of dependencies just waiting to snap at 3 a.m. on a Friday? The design choice is entirely up to you.